Hey everybody, I'm Lydia.
Hey, I'm Avery.
Hey, this is Catherine.
And welcome to PLIX CubeSats Online, our first session of 3. Just a couple things ahead of time, some upcoming PLIX online workshops. Next month in August, we'll be starting our community calls, and later in August and early September, we'll be running PLIX Urban Ecology Online, which maybe some of you joined us for in late spring. You can RSVP with this link here. We'll put it in the chat. And you can also RSVP to just be notified for future events. So our agenda for today, we're doing our welcome right now. Avery's going to give a short presentation on satellites, on CubeSats, and go through the overview of this first activity that you can run. Then we'll do breakout discussions and think about how you might run this activity remotely. And then we'll get back together and share our ideas, and the team can answer any questions. And just one thing before we get started, I wanted to thank you all for participating in the forum. If you've been with us before, you know that we usually do it in a Google slide deck, but we just launched the forum as a place for us to co-create this welcoming and collaborative space for the PLIX community of practice. And we're really excited to have you all as some of our first users. So thank you. All right, Avery, it's all you.
Great. So hello, everyone. Welcome back for another excursion with the PLIX team. Today, we're going to discuss the PLIX CubeSats activity series. I should first mention that CubeSats is a shortened term for cube satellites. And so this activity series consists of 3 different what we call missions or activities. The first is rapid prototyping, which we're going to discuss today, and this involves the design of a model CubeSat. Thereafter, we have a mission focused on testing the model satellite and also integrating a payload of patrons' choosing. A payload is a sort of functional aspect of the satellite, which allows you to collect data. And then finally is the liftoff, the actual gathering of the data. And we do this via a tethered balloon deployment. So that image on the right there is really what we're going after as a sort of apex of this series. So I wanted to highlight a couple of the reasons that we really like the CubeSats activities. First of all, they offer a sort of creative pathway for engaging with outer space, for connecting with engineering for outer space. So it can capture the interest of someone who's not traditionally interested in the mainstay technical elements of cube satellites and engineering. It also encourages peer learning and family learning and collaboration. A lot of the building processes are done in conjunction with other people. You're always sharing ideas, you're testing together. And so this really lends itself to a peer learning process. The activities support data literacy through allowing patrons to collect their own data, manipulate their own data, play around with their own data, share it with others, and really sort of get at the process of that data collection and manipulation. And finally, it's an entry point, we think, for discussing things like climate change or changes to the global, to the Earth. And we hope that the discussion of the technology sort of interfaces with these discussions about the sort of changing planet as well. So I want to talk a little about small satellites and their functions as background for this session. Small satellites are sort of a weird term, but it basically just means any satellite that is under 500 kilograms. So CubeSats or cube satellites are a type of small satellite, and they have all sorts of different functions that we're going to discuss. And in this week, in the making prompt that we all had to complete, you sort of got a taste for the different things that satellites and cube satellites can actually do in terms of taking images, remote sensing, and all of the different ways that these data sets are compiled. And I hope you enjoyed and had fun with that making prompt. So what is a cube satellite? So a cube satellite is basically just a very, very small satellite. It is 10 by 10 by 10 centimeters in the smallest unit, which is also called 1U. And these units can be stacked on top of each other, up to 24 units. And CubeSats were actually developed in the late 90s, early 2000s as an educational tool. So at Cal Poly San Luis Obispo University in California, these professors sort of realized, well, all these aerospace students, they don't actually have a chance to test their knowledge. And so they needed a platform to test out all the engineering skills in aerospace that they had been learning. And so CubeSats were developed. And so what the inventors didn't foresee necessarily is that CubeSats would become a staple in aerospace research and engineering. And has now become a sort of industry standard for engineering processes and exploring outer space. And there are a couple of reasons for this. First of all, CubeSats can be built rather quickly compared to larger satellites. So generally within 2 years, that's including testing time, integration, and all the paperwork involved, which is actually the hardest part. The tech is actually pretty simple for the most case, for most circumstances. All of the parts are generally commercial and off the shelf, so it's a lot modular in terms of assembly than conventional satellites. And along with that, the design is relatively simple in a lot of cases. The most important thing is that CubeSats are very, very low cost. And this has sort of enabled it to be a citizen science platform. So you see a lot more universities, even high school classrooms, starting to build CubeSats testing payloads. And this also makes it advantageous for university researchers because in a traditional sense, you couldn't really test out payloads you're developing or experiments or telescopes or what have you without like a 10-year mission and billions of dollars in funding. And now you have a 2-year timescale to work with in terms of testing out technology that's a little bit lower risk. So again, it's adopted for educational purposes, but we're increasingly seeing CubeSats emerge in scientific research, in commercial spaces, and in industry. And so the miniaturization, or really small size of CubeSats, is a great benefit, again, because of those reasons I listed, the cost and the modularity, but it's also a significant challenge. So traditional satellites are fairly large. So these are 2 examples. On the left is a communications satellite that is developed by Lockheed Martin. And then on the right is a satellite called JUICE, which is being developed by the European Space Agency. And you can see that these are massive. You see the people in those images. And so the ultimate challenge with CubeSats then becomes, how can we have this level of function, this amount of payload, distributed in either just one or multiple CubeSats? And so the answer sort of lies in the fact that we can launch multiple CubeSats at once. And so in general, a rule is that more CubeSats equals more coverage. So this is a diagram on the left showing the different types of orbits satellites can exist in. And so when we think of things like Landsat, which is an imagery satellite that gets us a lot of images for Google Earth, this is in something called geostationary orbit, which is depicted on the graph on the bottom right, where the coverage isn't so great because the satellite is effectively remaining in the same place along the equator. CubeSats are more likely to exist in polar orbit, which experiences more coverage of the Earth, but requires 14 days to actually cover the entire Earth. However, if you have multiple CubeSats in orbit, you don't need 14 days to cover the Earth. You can cover the entire Earth in 1 day. So immediately, because CubeSats are lower cost, because you can have more of them, you sort of see how their small size can be compensated for in terms of just developing this group of CubeSats, which is also called a constellation of CubeSatellites. And so how do we get a CubeSat into orbit? It's actually really cool. So these launchers effectively are bolted to wherever you can fit into a rocket. So you're going out for a mission, maybe you're replenishing something on the International Space Station, or maybe you're just testing out commercial spaceflight technology. Well, these boxes that hold CubeSatellites, these spring-loaded boxes, are bolted in place to virtually any corner of the rocket that you can find. Once you're in orbit, you can then transfer the CubeSat to a launcher. And so this is a launcher developed by a company called NanoRacks that's on the ISS. And you can see that once it's spring-loaded into the launcher, it just sort of shoots into orbit at the sort of right time. And this can be done maybe by an astronaut on board, but can also be done remotely on Earth using electronics and communication. So I wanted to highlight a couple of the functions of CubeSats, and I was able to use some of the images that you contributed in the forum, so thank you very much for that. And the first is remote sensing and imaging. So remote sensing is basically just, it's in the name, it's sensing something from very, very far away, in this case, space. Satellites are often used for tracking hydrological changes or changes to water patterns or the flow of water. So on the left, we're looking at a dynamic view of how the course of a river is changing over time. And then Dave from Michigan City Library in Indiana was able to contribute this time lapse from Michigan City, Indiana, actually depicting the changes noticed along the shorelines there. Another example of time-lapse imagery, or taking a series of images over time and noticing changes, was contributed by Audrey, and this is in Querétaro, Mexico, looking at urban development. And so we can use satellites, we can use the sort of changing images over time to either track changes to the Earth or even track changes to what people are doing in terms of urban development or deforestation or reforestation, or in this case, making green spaces and expanding cities. But satellites aren't only used to look at Earth, they're also used to look outward and into the galaxy. And one of the emerging functions of CubeSats is actually to discover exoplanets. And so CubeSats not only image things, but they can also be used as telescopes and actually pick up light from very, very far away stars and other galaxies to help us discover new planets. Finally, CubeSats can be used for communication. Not only finally, there are many other functions of satellites. These are just some examples, but communication is obviously super important. And in this case, CubeSats were actually launched to orbit Mars. So CubeSats don't only have to orbit our planet. And the reason for this is the InSight mission, or putting a rover on Mars, required extensive communication with Earth. There's a lot of sort of relay of signal going on. And this was actually made possible by deploying these two 6-unit, or 6 of those stacked 1-unit CubeSats into the orbit of Mars. So lots of different functions, lots of different capabilities, and of course, lots of different data coming out of these Cube satellites. And so the whole vision with the first CubeSats workshop is to sort of get at the process of building out one of these satellites. It focuses on developing a model cube satellite and also understanding sort of what we discussed, which is the function of small spacecrafts and a lot of the trade-offs associated with engineering something that is very small, that has to be space rigorous, but also has to complete a scientific mission. So the activity itself is composed of sort of 3 sections. The first is an introduction, which is to get at the question, what are satellites and how are they used? And what are small satellites and how are they used? And how do they differ from regular satellites? And so that is meant to be a sort of presentation by the facilitator, and goes over, or is intended to go over, all the ideas we just covered. So all the slides I just discussed and all those ideas are something that you can use to cover in this introductory discussion with your patrons in the workshop. There's then a main activity, and this is the rapid prototyping of model cube satellites. And there's an example on the right, rather advanced prototype. And then we have a come together, or a gallery walk, of sharing out prototypes and just circumnavigating the class or space or the library setting and discussing all of the engineering challenges. And so this workshop is actually fairly straightforward. We have a couple of facilitation tips that we think will really help the workshop run smoothly and be an engaging experience for all of your patrons. And the first relates to populating your space with a variety of examples. So as a facilitator, we of course encourage you to create a couple of examples ahead of time. And it's particularly important in this instance because although we are thinking about cube satellites, we want to leave the creative space open for people to explore different shapes or conformations of their satellite, whether it's a pyramid or a sphere or just using popsicle sticks. And so you as a facilitator showing that that's okay and that's possible is pretty important. And it's also helpful to have one cube that is generally 10 by 10 by 10 centimeters in size as part of the workshop is also helpful just to demonstrate and just to make it sort of tangible that that is the basic unit that you are working with. We also encourage you to set up your space to encourage collaboration. And so this exists in a couple of ways. You can set up the tables in a way such that it sort of fosters talking across the table, working with others, and also having all the materials there so people are sharing, they're asking questions, they're sort of engaging in that dialogue about what they're actually building out and prototyping. And this not only relates to physical space, but also to sort of the people in attendance. And this activity really, it works quite well for family creative learning or intergenerational learning. So we really encourage you to advertise or facilitate the workshop in a way that brings together patrons and their guardians or parents. In this case, it's also really helpful or can be insightful to engage outside expertise. And this falls in a couple of different ways. And the first is that, there are a lot of experts in aerospace engineering and satellite design, and we're not asking you to be experts in these domains at all. There are so many resources online that you can use, amazing videos and tutorials, a lot of NASA resources, NASA educational resources that you can use to supplement sort of what is going on in addition to the build. So if you want to start your introductory session with something like this video on crazy engineering, you can do that. And engaging outside expertise also relates to the idea that you can actually bring in researchers to supplement your sessions. So we've actually worked with Ballerup Library in Denmark, who partnered with Danish Technical University, and they were able to bring in researchers from the university who had expertise in engineering, not only to lead discussions, but to also sort of prompt and facilitate discussions regarding the design of the patrons' CubeSats, how they rose to those design decisions, and how they could be maybe improved or changed or iterated on in future cycles. So we wanted to sort of give you a seed crystal for thinking about running rapid prototyping at a distance. And this could include things like making a kit or a CubeSat starter pack, so to speak, that includes materials for at-home prototyping, but also maybe a curated series of books or video resources that relate or can spark some inspiration for the build of the satellite. You could post a mission prompt on social media and have patrons share out what they're building. Something that we've explored and what you actually are all gonna do next week in the making prompt is build your own Cube satellite to house a smartphone or to house something that is located around the home, or build a one-use satellite using household materials, and then having patrons share their results perhaps via social media. You could also choose to compile something like a gallery online or a catalog inspired by space or part catalogs. So you can have a CubeSat catalog to have patrons not only share their ideas, but you can have something to share back out with your community. And those are just a couple of ideas. And the breakouts, you'll all be brainstorming more about how to bring these activities to your patrons. So with that, we will head into the breakout sessions.
You should be seeing the breakouts open shortly, just below this window. And yeah, I think, we're here. If you have any questions, feel free to just ask them in the chat. All right, thanks everyone. See you back here in about 20 minutes.
Thank you.